Hello everyone. My name is Nazanin Ganjehzadeh and I'm a PhD student at the University of Toronto working with Professor Jakubiec. I'm so sorry for not being able to attend in person, but I'm grateful to have the opportunity to present my work to you online. Today I want to talk about my research methodology, which is about tracking human light exposure, health, and well-being by using data logging sensors and smartwatches. We've known for a while that light has significant non-visual effects on our body. These effects are critical for regulating our internal body clock, influencing our sleep, and maintaining our overall physiological state. Our body goes through different phases throughout the day, each designed to optimize how we function. In the morning, we usually feel most alert and ready for mental tasks. And as the day goes on, it's normal to feel a bit of an energy dip in the afternoon. Later in the early evening, we often hit a peak in physical energy. By nighttime, our body starts winding down, producing more melatonin to help us get ready for sleep. So understanding how light exposure affects circadian rhythm is critical in designing building environments that support occupant health and productivity. This image shows the difference between a healthy circadian rhythm and a disrupted one. On the left side, we see a person with a healthy circadian rhythm. The pineal gland produces melatonin at night, signaling the body to sleep. This regular rhythm ensures good sleep quality and overall health. On the right side, the circadian rhythm is disrupted by exposure to artificial light, like from city lights or screens. This interference delays melatonin release, leading to poor sleep quality and increased risk of sleep disorders and chronic illnesses. The potential health effects of disrupted circadian rhythms are poor sleep, increased risk of obesity, diabetes, depression, heart disease, cancer, and a weakened immune system, which often caused by irregular sleep patterns, excessive screen time at night, or shift work. Many studies examine how light exposure during the day and night affects the risk of psychiatric disorders and self-harm. Being exposed to more light at night is linked to a higher risk of issues like depression, anxiety, PTSD, psychosis, bipolar disorder, and self-harm. On the other hand, getting more daylight is connected to a lower risk of these major mental health problems. So avoiding light at night and getting plenty of daylight during the day could be an easy and effective way to improve mental health without needing medication. This image shows how light influences both our vision and our circadian rhythm. When light enters the eye, several factors known as mediating factors determine how this light impacts us. These include the timing of when we see the light, its intensity, the wavelength, how long we're exposed to it, and our past experiences with light. This light is processed by the retina, where special cells called intrinsically photosensitive retinal ganglion cells, or IPRGCs, and you take this light and send signals to different parts of our brain. By sending signals to the suprachiasmatic nucleus in our brain, this area controls our sleep-wake cycle and influences our alertness and melatonin suppression. These IPRGCs are unique photoreceptors. They're not just for vision, they mediate non-visual responses to light that affect our circadian rhythms, sleep, alertness, mood, and cognitive performance. IPRGCs contain melanopsin, a photopigment sensitive to short wavelength blue light. The left image shows the difference between the visible light spectrum and the circadian light spectrum. The circadian spectrum focuses on the blue light wavelength range that most affects our circadian rhythm, regulating our sleep-wake cycle and overall health. And the right image shows how our visual system responds to light over time. The top right section shows how we perceive a scene visually, while the bottom part breaks down the different types of photoreceptors in our eyes, cones for color vision and melanopsin-containing cells for circadian regulation. Factors like light intensity, timing, duration, pattern, light history, and wavelengths all play a role in how light affects non-visual photoreception. For instance, exposure to short wavelengths, enriched blue light before bedtime can enhance alertness and performance, but disrupt subsequent sleep. By recognizing IPRGC's role in physiological and psychological health, researchers have developed quantifiable metrics to capture light's effects on these cells. Metrics like melanopic radiance measure light and melanopsin sensitive wavelength range. Others like Equivalent melanopic light lux and melanopic to photopic light ratios account for light spectral composition and its effect on RPRGC activation. These metrics help create tools and models predicting daylight's non-visual effects and evaluate built environments in promoting health and well-being. The well-being standard was designed as a global framework to provide guidelines for circadian lighting design and optimize indoor environments for human health and well-being. But recent research emphasizes the need to shift from room-based metrics to human-centric lighting metrics. And this shift assesses movement between multiple indoor spaces and the outdoors, focusing on the non-visual effects of light on occupants. Moving from metrics to applications, we see innovative simulation tools and architectural design approaches have been developed with the goal of using these metrics that enhance our interaction with light, particularly from a non-visual perspective. Moving from statistic architectural lighting analysis to dynamic evaluations, the focus has shifted towards how individuals interact with their environment. This shift towards human-based evaluations emphasizes the need for personalized lighting strategies that show the diverse behaviors and preferences of occupants. Lastly, technological advancements allow us to track and analyze light exposure in real-world settings. The evolution of wearable sensors has been a game changer in measuring light exposure with precision. As you can see in these images, devices range from wrist-worn sensors to near-corneal instruments, enabling detailed tracking of the spectral, temporal, and intensity dynamics of light. Ganjehzadeh and his colleagues use smartwatch technology to capture real-time occupant comfort data. They Cozy Fitbit application captures large-scale data with minimal intrusion, supporting environmental adjustments based on individual comfort preferences. The development of these tools helps us to explore the complex dynamics of light interaction with human biological systems that enhances our understanding of light's physiological consequences. In this presentation, we introduce a methodology for field measurement of IPRGC influence lighting on humans regarding their self-assessed health and well-being, especially the role of lighting conditions on human physiology and psychology. This methodology assesses the impact of architecture on its occupants' health by shifting the focus of lighting analysis from building spaces to transient occupants. Traditional room-based metrics mainly focus on whether a room or space meets specific EML threshold values for lighting using fixed view or work plane sensors within a space. However, these metrics may not fully capture the impact of dynamic lighting due to control systems, daylight behavior, transit, and the use of multiple spaces on circadian rhythms and human well-being. In contrast, human-centered lighting metrics may take into account the non-visual effects of lighting dynamics based on the activities and choices of the occupants being analyzed. Our goal here is to explore the temporal and spatial dimensions of light exposure. In this regard, we want to gather real-world data on how light exposure affects individuals as they move through different spaces. This figure illustrates our data collection process. I'd like to walk you through this methodology. As you can see, this setup gives us a multidimensional view of each participant's environment and how they interact with light throughout their day. We aim to create a comprehensive analysis by collecting continuous measurements of spectral light exposure. This involves not just the intensity, but the quality of light that participants are exposed to throughout their daily routines. To achieve this, we equipped participants with a custom light sensor, which records a spectral irradiance for the calculation of melanopic-based metrics. Alongside these sensors, participants wear a smartwatch with custom firmware. These watches serve dual purposes, tracking physical activity and sleep pattern and administering surveys. Additionally, participants are asked to keep a daily journal about their activities and schedules, sleep quality, and self-assessed well-being metrics that complements the raw data from the sensors. The primary goal here is to link light exposure directly to key health outcomes like sleep quality, mood, and alertness. In this project, we used this data logging melanopic radiance sensor, enabling us the evaluation of light exposure impacts for different individuals who occupy the same spaces. This is a wearable open optical spectral irradiance sensor, or we call it USI, developed by Professor Jakubiec and his students to track personal lighting levels and measure electric lighting levels in the spaces. The OC sensor can be worn by an individual, clipped to their shirt, or using a necklace. It can also mount on a tripod and collect data for extended periods of time at a fixed location. This sensor is designed to measure the power distribution of visible light across individual wavelengths, allowing for the identification and quantification of topic and IPRGC influence light qualities. It is capable of measuring spectral power distribution at 5 nanometer intervals between 340 nanometer to 1010 nanometer. In terms of spectral data, the OC sensor can identify light sources such as fluorescent, daylight, and LED, as well as determine color temperature and melanopic and photopic units under CIS 026 standard. Each participant in our study wears the OC sensor for 2 weeks. Why 2 weeks? This duration allows us to capture a comprehensive view of each person's typical patterns and habits and how unexpected life events or disruptions can affect their normal routines. This sensor records the spectral light exposure every 1 minute. This allows for continuous long-term data collection in various environments, including the participants' residences and offices. You can see 9 days of the recorded light exposure data for 1 participant in these images. And the left image here shows the example of daily spectral irradiances, and the right image shows the example of daily melanopic irradiance measured by the OC sensor worn by the participants. By tracking these fluctuations in light exposure with such precision, our goal is to discover how the timing, intensity, and quality of that light interact with their daily lives. In addition to the OC sensor, participants wear a Fitbit smartwatch continuously for the same 2-week period. Because of our specific research needs, I developed a custom clock face called Cozy Light based on the Cozy clock face developer code. This customized clock face was specifically designed to gather the most relevant data to our study, and it was installed on a Fitbit smartwatches used by participants. This smartwatch enables us to track not only physical activity, but also detailed sleep patterns and subjective well-being. It monitors various sleep stages, including light sleep, deep sleep, and REM sleep. It can also identify periods of wakefulness and calculates the total duration of sleep. This data gives us insights into each participant's sleep quality. And the other use of the Fitbit is to deploy periodic surveys. The questions you see in these images are programmed to pop up at 4 specific times throughout the day: 8 a.m., 12, 6, and 10 p.m. Each survey consists of 4 to 5 questions, depending on the time of day, asking participants about their current alertness, mood, recent activities, screen usage, and bedroom lighting conditions. This dual approach using both the OC sensor and the Fitbit smartwatch allows us to capture a comprehensive snapshot of each participant's light exposure, sleep patterns, and subjective well-being. We don't just rely on sensors to tell us the full story. Each participant maintains a daily journal using a spreadsheet we provide, as you can see a part of it in these images. In this journal, they document several key aspects of their daily lives. Sleep patterns include sleep times and quality, which complements the sleep stage data from the Fitbit smartwatch, light exposure experiences throughout the day, like what kind of light they were exposed to, how it made them feel, and any notable changes in their environment. Alertness levels and mood at various times throughout the day, and lastly, general locations during each day at hourly intervals. This spatial data lets us see where they spend their time and how their environments might influence their light exposure. By combining these qualitative journal entries with the quantitative data from our sensors, we conduct a holistic analysis of the interplay between environmental light, human behavior, and circadian health. After collecting all the data from participants, we outline a plan to analyze the relationships between light exposure, activity patterns, sleep quality, and subjective alertness in daily life. And let's see how we approach this analysis and what we aim to discover. Our goal is to understand how exposure to different levels of melanopic irradiance affects individuals' a subjective sense of alertness, health, and well-being. This includes exploring the effects of different times of day and locations on melanopic irradiance levels. We'll also explore how individual light schedules relate to alertness and melanopic irradiance, helping us understand how personal lifestyle choices influence health and well-being. However, we also expect significant variability due to individual and temporal factors. This analysis plan is designed to be both comprehensive and reproducible. So let's see how we visualize these relationships on how IPRGC influence lighting impacts subjective alertness throughout the day. Fitbit smartwatches collect self-reported alertness at 4 key times throughout the day. Alertness is captured through predefined categories, a little tired, alert, and sleepy. This allows us to quantitatively analyze the link between light exposure and subjective alertness. This image shows the relationship between average melanopic irradiance exposure measured by the UC sensor and self-reported alertness from the smartwatch for 3 participants out of 15 with varied sleep habits and light exposure patterns. The points on the plot are color-coded to indicate these 3 levels of alertness. And the size of each point correlates with how frequently participants reported each alertness level. Larger points indicate more common experiences of alertness at those times. Our analysis framework helps us identify clear trends and fluctuations in how light exposure impacts perceived alertness. For example, here, participants report being alert when they experience higher levels of melanopic irradiance during the day. However, this is inconsistent across all times. Participants often report being sleepy in the afternoon and evening, despite higher irradiance levels, indicating that factors other than light also influence alertness. Each participant shows a unique pattern of alertness throughout the day, influenced by the individual schedules, natural circadian rhythms, and the specific activities they engage in at different hours. In our example, participant 2 is relatively high in alertness with a high melanopic irradiance at 8 a.m., while participants 1 and 3 peak in alertness at 12 p.m. Moving forward, it's clear that we need to consider individual differences and the complexity of factors affecting alertness beyond just light exposure. This plot shows how daily schedules and different times affect light exposure among the participants. For example, during the day from 6 a.m. to 6 p.m. on the left plot, we observe a higher level of melanopic irradiance across all locations. This is expected due to presence of natural daylight and the use of electric light in work and home environments. At night from 6 p.m. to 6 a.m. on the right plot, there is a noticeable drop in irradiance, reflecting the diminished light exposure typical of nighttime. The unexpected higher home irradiance levels for participant 1 in yellow and the lower overall exposure for participant 3 highlight the need for personalized lighting design and health recommendations. This plot and our findings show the complexity of human light interactions and the importance of considering individual differences and environmental conditions when evaluating the effects of light on health. This plot shows the typical sleep durations for the participants. Each horizontal bar represents the span of time during which each participant is typically asleep, marking from their average bedtime to their average waking time. Sleep schedules might explain variations in alertness, as previously shown. For example, participants might naturally report feeling more alert following their average wake-up times, having just ended their rest period. Conversely, as participants approach their typical bedtimes, self-reported alertness could decrease. This is consistent with the natural decrease in alertness as the body prepares for sleep. The length and quality of sleep can significantly influence alertness levels during the day. For example, a participant with a longer, more consistent sleep pattern might exhibit higher alertness levels, as sufficient rest can enhance cognitive function and mood. Here is an example of the comparison between two of the participants. A participant with an early wake-up time, like participant 2, would be exposed to morning light, potentially improving their alertness and mood. In contrast, participants who wake up later, like participant 1, may miss out on this crucial exposure, which could affect their alertness levels differently. And this analysis of sleep durations, when combined with our findings on light exposure and alertness, underscores the complex interplay between these factors. This image presents a comprehensive chart detailing participants' responses across various well-being indicators, such as sleep quality and any reported disturbances and sleep anomalies, number of awakenings, and nap times. We observe how much time participants spend in well-lit areas and their reliance on artificial light. This is connected to their reported productivity levels and consumption habits before bedtime. We also ask about their morning alertness, mood, and daytime sleepiness levels. This helps us assess how subjective sleep and wake experiences relate to exposure to light, daily routines, and overall mood. Each color pattern in the chart represents a different response category, making it visually intuitive to grasp the spread and frequency of these self-reported measures. And this visual data representation of the 3 compared participants and our analysis show how self-reported well-being is deeply intertwined with subjective measures of light exposure and activity patterns. By understanding these relationships, we can better tailor interventions and recommendations to improve health outcomes based on individual needs and experiences. For instance, we analyze and compare the sleep quality and mood of these 3 participants. The data suggests a relationship between sleep quality and mood. For instance, participant 2, despite experiencing poor sleep on several occasions, reports a high percentage of happy moods, suggesting other resilience factors or compensations during the day. Participant 3's higher fair sleep quality responses correlate with a predominantly neutral mood, indicating that their average sleep might be impacting their ability to feel more positive or energized during the day. Participant 1's varied sleep quality and the highest reported rate of upset mood might suggest a closer relationship between their rest and emotional state, where poor sleep could be directly affecting mood more significantly than in other participants. It's important to note that this is just an example of how we might analyze the data, not the actual results of our research. The purpose here is to demonstrate the kinds of insights we can potentially find by examining the relationships between light exposure, sleep quality, mood, and other factors. These analyses allow for better approaches that can address specific areas of concern, whether it's improving sleep hygiene, managing stress, or adjusting light exposure to enhance mood and circadian alignment. In our study, we introduced a novel data collection methodology to evaluate the impact of light exposure on health and well-being using wearable sensors, smartwatches, and daily journaling. This approach allows us to capture both objective measurements of light and subjective well-being assessments. So far, we hired 15 participants, which we showcased the data from just 3 of them in this presentation. And we aim to expand our research to have 80 participants to include a more diverse cohort, enhancing our insights into the relationships between light exposure, health, and well-being. Despite some challenges like participant compliance and the subjectivity of self-reported data, our methodology offers a foundational approach for future studies aiming to refine our understanding of light's multifaceted effects. By continuing to collect and analyze data, we want to develop adaptive and personalized lighting strategies that improve daily living and public health outcomes. I want to thank you all for your time and attention, and I'm happy to take any questions or comments you may have. Thank you.
Thank you. Are there any questions? Oh, Greg has one. I didn't see.
I was just curious, nice presentation. Curious what kind of sleep quality measures you were getting, and then were they based on the smartwatch, or do you have some other way of measuring individual sleep quality?
Actually, we get the data from the smartwatch and also the subjective the survey that we asked from the participants. So the smartwatch itself record the smartwatch itself record their sleep quality as they're experiencing a light sleep or deep sleep or whatever. And also we asked them about their sleep quality in their daily journaling here. We
Right.
asked them, for example, did they sleep well, or do they have any like sleep disturbances or anything? So we have like kind of different
I understand.
measures by
correctly.
sleep quality.
Did the smartwatch also measure the light levels somehow, or did you
No.
have a separate device for that?
No, we have the light sensor, the US sensor here. This sensor, it records
Okay, so
all
that was the
the
unit you
light
were
exposure.
using. And they
Yes.
presumably set that on the nightstand in the evenings and when they went to sleep.
Yeah, yes, they wear this sensor like for whole day, just except for nights. They should wear it morning until before their bedtime.
Okay, thank you.
Yeah.
Nice study.
Thank you.
Thank you. It's a very interesting presentation. What was the age group of your participants? And like, did you see that they were compliant enough to do the survey 3 times across 2 weeks? And also, were you measuring like the ambient lighting by any other way than the one like this device you have for the personal lighting collection, personal light sensor that you have? And how did you know like where they were at different times of the day? Like, or you were using the journal for that?
Thank you
Sorry.
for the question. For the first one, we actually, our pool of participants are university students. We are asking U of the master and master of architecture students. So the age is average between like 22 to up to 30 years old. And regarding the ambient light, yes, this sensor can record the light exposure no matter where they are. So it can record like daylight, electric lighting, and all the light exposure that they are actually exposed to. And regarding where they are during the day, we asked them to fill out these journals. So at hourly intervals, we ask them to fill out this journal, for example, where they are, like general locations, if they are at homes or schools, or for example, they're outside for shopping or anything. So we gather the like general locations of where they are. But we can use the light sensor data too, because it can record all the light spectrum. So I think I can answer.
Go ahead. I'll just take it all.
Okay.
Yeah, so just to add to that a little bit, well, I was trying to speak into the mic here, but
Well, this one too. So
oh, okay, all right. So, anyways, just to add to that a little bit, the smartwatch connects to the cell phones that the participants use, and so we could theoretically get GPS coordinates, but we didn't try to sneak that one through the ethics review board. I felt it would have been challenging. What was the other one I wanted to say? Oh yeah, it's earlier when we were testing this instance out, Nazanin measured, like, she wore a sensor and then measured the PhD studio and her home like independently, and so she was able to compare like the circadian related metrics for the core spaces she occupies versus like the effects of her own behaviors. But like in this study, we're not doing that. Who else has to?
Oh yeah, I have a quick question about like which variables you control to isolate the impact to just light. Like, did you have like expectations of like they're not allowed to drink caffeine during this time, or even like things like alcohol that might affect sleep and alertness?
Actually, we don't have any criteria to limit our participants. The goal here is to capture the real world behavior and whatever they experience during the day. But regarding the consumption, yes, we in this journal, this question here, we asked them if they, for example, consume caffeine or alcohol or even light meal or very heavy meal before their sleep. So they can choose between these options here for all 14 days.